Hi everyone. In this lesson, we'll be studying a technique called the chain rule, which is a technique to differentiate compositions of functions. Let me explain what that means. So, for example, suppose we have a simple function like u of x equals 5x minus 7. We already know how to differentiate that, right? The derivative would be 5, right? And suppose we have a function, say f of u equals u to the 10. I use a different variable, but in essence, we know how to differentiate the 10th power function. You bring the 10 down, subtract 1 from the power. So the derivative for that one with respect to u would be 10u to the 9, right? Now, what if I put those two together and create a more complicated function, a composition of those two functions, something like f of u of x. So f in terms of x, so something like 5x minus 7 to the power of 10. Now that we have not yet learned how to differentiate. The only way we know how to do that is to expand that to the 10th power, which will be incredibly long and tedious, and then we can differentiate it term by term. Of course, we don't want to do that. We're looking for a simple way to differentiate compositions of functions, and the chain rule will be the answer to that problem. So let me show you, first of all, the rule, and then we're going to do lots of examples. So let's say that I have a function y is in terms of u, and then u is in terms of x. And if you're trying to figure out what is the derivative of y with respect to the last variable x, what you do is you do it in steps in a sense. The chain rule tells us differentiate y with respect to u first, find that derivative, and then differentiate u with respect to x, and then you're going to multiply those two derivatives with each other. So here is the general rule, dy dx equals dy du times du dx. And if you think about it, like almost makes sense. Like if these du could have been canceled, like on this side you have dy dx, on this side you're going to end up with dy dx, right? So again, there could be a complicated proof for this using the definition of derivatives. But for the moment, again, this is just an intuitive explanation about why the rule works. And if we rewrite this again, so dy du, remembering that y is a function of u, so dy du would be the derivative of that, which is f prime of u. And then du dx, since u is a function of x, u is g of x, the derivative of that would be g prime of x. And since u is the same as g of x, we can put that in here for u, replace u by g of x, and voila, we have the final version of the chain rule. I know it may look complicated at first, but once we do the examples, you will see it's not that bad. So let's repeat then. So if your y is a function of u, is a function of x, and you're trying to find the derivative of y with respect to x, the way it turns out is f prime of g of x times g prime of x. And this is important. Here, the same rule stated in plain English. To take the derivative of a composition of two functions, first take the derivative of the outside function, which was f, because we had basically we have y equals f of g of x. So take the derivative of the outside function, which is f, leaving the inside the same, so g of x stays the same. Then multiply this by the derivative of the inside function. Inside function is g of x. We're multiplying everything with the derivative of g of x. So that's what the chain rule is. And now we can revisit our example from the top. If you had something of the form 5x minus 7 to the 10th power, what would the derivative be? So I'm just going to call that the g of x function, or let me just say y equals 5x minus 7 to the 10th. What would be the derivative of that function? So you differentiate the outside function, that's the power of 10 function. So bring the 10 down, subtract 1 from the power, leaving everything on the inside the same. And then by the chain rule, you multiply everything by the derivative of the inside. So you multiply it by 5. And in simple form, you can multiply 5 times 10 is 50 times 5x minus 7 to the power of 9. So you see how much easier this method is. Contrast that with the former method where you would be forced to expand 5x minus 7 to the 10th power. Again, that would be like take us all day. So this is definitely going to save us time. And let's begin with example 1. And I'm going to leave this as an exercise for you to do later where you can expand 2x plus 1 squared, take the derivative, and use a chain rule to take the derivative and verify you're going to get the same answer. Because here the power is small, you can do it both ways. Okay, so for now, let's take a look at f of x equals 3x plus 5 to the third power. What is the derivative? So this is very much like the example we just did, right? So differentiate the outside function, leaving the inside the same. So it's like 3u squared type of thing, right? Leaving inside the same. And then multiply this with the derivative of the inside, which is 3. At that point, we can combine those constants laying around. Now we have 9 times 3x plus 5 to the power of 2. Usually you're not going to have to expand the result. You can leave it like that. Okay, what about example number 2? F of x equals quantity 6x squared plus 4x to the 5th power. Let's take the derivative, again using the power rule. Bring the power down, leaving inside the same. So differentiating the outside function. Remember, it's like u to the 5. It's of the form u to the 5. So the derivative will be like 5 times u to the 4. And the u is staying the same, the inside part is staying the same. And then multiply everything with the derivative of the inside, which is 12x plus 4. So we can leave it like that. Or if you want, you can distribute the 5 with that quantity, or you can even factor a constant. So there are multiple ways to do it. I would accept this as a correct answer in this form. But if you like, you can also take out a 4, multiply with the 5 up front. So that will give you 20 times 6x squared plus 4x to the power of 4. And if you take out a 4 from that last part, so divide by 4, so you get 3x plus 1. So that would be another way to leave the answer. Now what about something like number 3? So it's going to be very similar, but instead of a whole number power, we have a fractional power of 1/2. It would help to write it first of all as x squared plus 1 to the power of 1/2. And from there, we're going to apply the same property. So again, it might be a great idea for you to try this first and check your answer with us. So I brought the power down, subtract 1 from the power, and multiply everything with the derivative of the inside. In this case, 2 and 1/2 can be simplified, so there's an x left on the top. And because I have a negative exponent, we have learned to leave the answer with a positive exponent. Like that's the format that I'm asking you to leave your answer. So let's bring it in the denominator then as x squared plus 1 to the power of 1/2. So that's the same as the square root of x squared plus 1 in the denominator. Okay, now the next few examples are a little bit different because we've been concentrating on the power function so far. What happens if you have a trigonometric function? So sine of 2x minus 3. Notice this is not a product. Like this is not to be confused with sine x times 2x minus 3. Right? This is more like example number 3, square root of something or sine of something. So your outside function is sine, your inside function is 2x minus 3. So we're going to start differentiating the outside function first, leaving the inside the same. Derivative of sine is cosine. So it will be cosine of 2x minus 3 multiplied by the derivative of the inside. Derivative of 2x minus 3 is 2. I can multiply it at the end, but I will put that up front. So the answer is 2 times cosine of 2x minus 3. So you can see how it's going to be very important to know your basic rules, because here you assume that you know the basic rules, but you're doing compositions of all kinds of functions, including the trig functions. For example, do you remember how to take the derivative of a tangent function? If you said secant square, you're absolutely correct. So again, start by taking derivative of the outside one. So it's going to be secant square of the given argument 3x squared minus 7. So we left the inside the same. Don't forget, by the chain rule, we multiply everything with the derivative of the inside, which will be times 6x. And let's not be tempted to multiply this by that, because 3x squared minus 7 is inside secant square function. So it cannot be multiplied with anything that's on the outside. I would say to avoid that temptation, it's better to leave it like this. 6x times secant square of 3x squared minus 7. So I put that up front, so clearly showing we don't want to multiply them. So what about something like number 6? It looks very different, like 1 over x cubed plus 3 to the 4th power. Like it looks like maybe we're going to need a quotient rule. But because the top is just a number, we don't really need a quotient rule, although you could use it. But you're going to need the chain rule along the way anyway. But I will prefer to write this as, to begin with, x cubed plus 3 to the altogether to the power of negative 4. So now it looks just like the power rule examples like we did 1, 2, 3, right? So let's look at the outside function as the power of negative 4. We're going to differentiate that first. So bring that down. Leave everything inside the same to 1 less power. So negative 4 minus 1 is negative 5. And because the inside is another function, it's not just like x to the negative 4, right? So when you have that, the chain rule kicks in. You will multiply everything with the derivative of the inside, which is 3x squared. And once again, let's write it without a negative exponent. On the top, we have negative 12x squared all over this quantity to the power of negative 5. Let's bring it down as quantity x cubed plus 3 altogether to the power of 5. So we will leave it as just like that, negative 12x squared divided by x cubed plus 3 altogether to the power of 5. Okay, what about number 7? Notice it will be very similar to number 6. So I would begin by rewriting it as 5 times that denominator to the power of negative 1. So 5 times x squared plus 3x minus 8 altogether to the power of negative 1. And now applying the chain rule. So bring the power down, get negative 5. Leave the inside quantity the same to the power of negative 2 times the derivative of the inside, 2x plus 3. Once again, rewriting our answer as negative 5 times quantity 2x plus 3 all over x squared plus 3x minus 8 to the power of 2. That's all in the denominator. All right. Let's take a look at 8b at the moment. I may come back to 8a later or provide a solution to you in the notes. So let's take a look at 8b and number 9. Those are going to be interesting ones, a little bit different than the ones we've done so far. So notice 8b is again a quantity to the power of 3. So your outside function is the power function of 3. But on the inside you have a quotient, x minus 1 over 2x plus 3. So when it's time to take the derivative of the inside, guess what? We're going to have to use, as you may have guessed, the quotient rule, right? So let's begin. Start by differentiating the outside function. So 3 times, leave the inside the same to 1 less power to the second power times the derivative of the inside. Okay, for the derivative of the inside, I know I'm going to have to use the quotient rule. And there I know with the quotient rule, the denominator becomes whatever you already had to the second power. So remember, we're looking at this inner portion. We're taking the derivative of that using the quotient rule. So we have like our little remembering method, like low d high. So the lower times there to higher, it has to be in that order, right? Because there's a minus in the middle. So 2x plus 3 times 1 minus high d low, higher times there to lower. There to lower is 2. And then all I have to do is really combine this quantity and expand it a little bit. So let's do that on the side, and then we can write our final answer down below. So we have 2x plus 3 times 1, that's 2x plus 3, minus 2 times x, so minus 2x. And don't forget to distribute the negative on the last term also. Negative 2 times negative 1, that's positive 2. Notice the plus and minus 2x will cancel, and our answer is 3 times quantity x minus 1 over 2x plus 3 to the second power. And on the second part for the fraction, we just have a 5 divided by 2x plus 3 to the second power. Now, it is possible to simplify this a little bit further. So for example, in the middle here, you can think of it as x minus 1 to the second power over 2x plus 3 to the second power. So if I think of it that way, and then 3 times 5 is 15, I can multiply them. So now I'm going to have x minus 1 to the second power divided by, notice the bottom will be 2x plus 3 to the second, but you also have 2x plus 3 to the second on the second fraction, and they're being multiplied, so I can combine them simply as 2x plus 3 to the fourth power. So this is another possible way to do it. But if you let it like this, if you just combine the 3 times 5 as 15 over 2x plus 3 squared times the original quantity, the x minus 1 over 2x plus 3 altogether to the second, that would be okay with me. But sometimes the question might be multiple choice, or you may be checking your answer. So it's important for you also to recognize that these two answers are exactly the same. So it can be written in alternate forms. Okay, another interesting example about the chain rule. Let's see, what happened to my notes here? I can do Control C. There we go. Okay, I'd like for you to think about question number 9. See how you would go about doing that one, and in a moment we're going to discuss it together. So for number 9, again, we have an outside function, which is a square root function. So we have square root of x times tangent x, which can be written as x times tangent x to the 1/2 power. So once again, we see clearly the outside function is the power function of to the power of 1/2. But on the inside, we have a product. So when it's time to differentiate the inside part, we're going to need to use the product rule. So let's begin. If this quantity is equal to y, then y prime equals, so differentiating the outside one, so you have 1/2 times x times tangent x to the power of -1/2 times the derivative of the inside. Okay, for the derivative inside using the product rule, I'm going to write the first times the derivative of tangent, which is secant square x, plus the second tangent x times the derivative of the first, which is 1. So that's really all we can do there. And the only other thing I'm going to do is simplify it by getting rid of the negative exponent and putting that as a positive one in the denominator. So on the top, you're going to have x squared secant x plus tangent x, everything divided by 2 times, and when you bring the other quantity down, it'll have a power of 1.